My name is Kovács Márton and I am a PhD student at ELTE Chemical Kinetics Laboratory. My research area is testing and development of detailed combustion reaction mechanisms. In combustion chemistry research, it is a common task to test such mechanisms against experimental data, either because you want to assess how published mechanisms are able to reproduce your recent measurements, or you wish to validate your new or updated mechanisms against existing experimental data. In this video, I'm going to show you that using the tools developed in our group, this task can be completed fairly easily. There are several widely used combustion simulation codes like Chemkin, Cantera, FlameMaster and OpenSmoke++, just to name a few. These codes are all able to simulate the so-called canonical combustion experiments like shock tube, rapid compression machine, perfectly stirred reactor or tubular reactor experiments. Also, these codes can calculate laminar burning velocity and species profiles in burner-stabilized flames. The results of these types of measurements are called indirect experimental data. In other types of measurements, the rate coefficients of elementary reactions are determined in a direct way. A practical problem that the simulation of these experiments require different input data files and keywords. Also, the format of the data files and the keywords are different in each simulation code. This is why we developed a simulation framework, Optima++. This program interprets a unified input data file, and currently it is able to use two different simulation codes. The usual way of testing a detailed reaction mechanism can be a complicated process. Experimental conditions and results are collected in Excel sheets, input files of the actual simulation codes are created, and separate runs are started for each experimental data point. The results are extracted from the output files of the simulation codes, and a separate plotting program is used to evaluate the results. These steps are very tedious, and many of them have to be repeated manually when something is changed. The offer here is another approach. The experimental conditions and measurement results are encoded first in an XML data file. Optima++ can read several XML data files in a single step, carries out all the simulations using a selected simulation code, reads the output files of the simulation codes, and compares the experimental data and the simulation results. The comparison can be in the form of traditional plots or by calculating an error function value that shows the agreement between the experimental data and the simulation results. Professor Michael Frankla at the University of Berkeley was the first who recommended the usage of XML data files for the storage of combustion experimental data. The data were stored using the so-called PRIME Kinetics data format, and large amount of data were published in the PRIME website. However, our group found that some experimental results cannot be encoded in the original PRIME format, therefore we created a modified version. This modified XML data format is called Respect Kinetics Data Format, or RKD in short. The latest version is RKD format version 2.2. The RKD format files are not compatible with the original PRIME format data files. The exact format of the RKD V2.2 files is defined in the following document. XML is the acronym of Extensible Markup Language. It is a markup language that defines a set of rules for encoding documents in a format that is both human-readable and machine-readable. RKD format files can be produced using program Optima++. However, this is a longer story and it will be a subject of another video. In the examples presented here, the RKD format files will be downloaded from the Respect information site. Respect is an information system that was created and is maintained in the collaboration of two research groups in the Institute of Chemistry of ELTE. Anyone may use Respect free after a registration. For the registration, providing an institutional email address is required. The Respect information system deals with three related areas: reaction kinetics, spectroscopy, and thermodynamics, and accordingly has 3 branches abbreviated with RE, SPEC, and TH. Now I log into the reaction kinetics branch of SiteRespect and look up methanol ignition delay data measured in ShockTube. If we click on the reaction kinetics branch, the site asks for a username and a password. After logging in, we can see the content. Now I will go to the indirect experimental data page. In this page, we can search in the database using several searching criteria, for example, species in the initial mixture, temperature, pressure, or bibliographical information. Let us look for methanol data, so I will type CH3OH into the initial mixture field. In the experiment type drop-down menu, I select ignition delay measurement. I will search for experiments published in 2016 to reduce the number of results. After clicking on the search button, the matching XML files will be listed in a table. If I click on the name of the XML file in the first line, it shows the content of the file in a human-readable form. An ArcID file stores the information between starting and ending tags. For example, the information about a physical property of the experiments should be defined inside a property tag. The actual name of the property should be given with the name attribute. In this case, the initial composition property contains nested component elements, and the number between the amount tags is the amount of the corresponding species in the initial mixture. While the units equal mole fraction attribute means that the unit of the composition is mole fraction. Now I download this XML file using the Save As option in the right-click context menu. Now let us go back to the Respect site and navigate to the Mechanisms page. We may look for a mechanism under the Collection of Recent Methanol Combustion Mechanisms tab. I download the .imp file of the Lee 2007 mechanism. In the following steps, we will use computer program Optima++. If you click on the Computer Programs page, the latest release is available under the Optima++ tab. I have now the necessary XML experimental data file and the methanol combustion mechanism. In this computer, Optima++ has been installed. Optima++ is a framework program. This means that it organizes the input and output files and controls the parallel running of the simulation codes on a computer cluster. Optima++ doesn't include a simulation code, and it uses external simulation codes. Currently, Optima++ may use Simulation Code FlameMaster and OpenSmoke++. These are freely available codes that can be downloaded from the website of the Aachen University and the Politecnico di Milano, respectively. Now, I run Optima++ for testing the Lee 2007 mechanism with selected experimental data. As you can see, the downloaded mechanism and XML files have been copied into the mechanisms and XMLs folders, respectively, in my Optima++ installation. I show testing mechanisms with the graphical user interface of Optima++. To set up a mechanism testing job, I click on the Simulate Experimental Data button. In this window, we can specify the location of the mechanism file. Now, we can select the solver to be used. I just leave OpenSmoke++ selected. I set the thread limit to the number of CPU cores to be used in my computer. We can read the XML files downloaded from Respect if we click on the green Add button. I have downloaded 3 XML files and I will use all the 3. The first file is a gesture reactor measurement. If I double-click on the name of the XML file, a new window will pop up where we can get some information about the data stored in the file. In the point list, we can select which points will be simulated. In the next table, we can specify the standard deviations of the experiments for each data point separately. I have collected the standard deviations in this table, so I can just copy and paste the values into this window. These values are absolute errors. I change the sigma scale to ups and set the unit to mole fraction. The second XML file is an ignition delay measurement in ShockTube. I assign 10% relative error for each experimental data point in the XML file. The last file contains concentration time profile measurements in flow reactor. I quickly copy and paste the error values here. And finally, we can click on the Start button to evaluate the calculations. Optima++ prompts for a file name where to save the input file. And now the simulations are running. Having all simulations finished, the results are immediately shown in a pop-up window. This table contains the experiment ID, the point number, the name of the measured species, the measured data, and the simulated results. We can jump to the next dataset in this table by clicking on the arrow button in the toolbar, or by the Shift plus down arrow keyboard shortcut. So these are the ignition delay measurement results, and from here the simulated concentration time profiles are listed. As you can see, we have 43 failed simulations. The reason is that experimental data are available for the concentrations of species C2H2, C2H4 and HCOOH, but species are not included in the Lee 2007 mechanism. We can copy the result to the system clipboard by clicking on the copy button in the toolbar. This way, the results are available for other applications. The results can also be visualized by Optima++ using the Plots tab. As you can see, the simulated concentration profiles and ignition delay times are in very good agreement with the experimental data. This can be quantified by calculating the error function value. This is automatically done by Optima++ if we provide the standard deviations in the input file. The calculated error function value for the 3 investigated XML files is around 6, which means that on average the simulated results are within 3 sigma errors of the experimental data. The error function values can be further investigated by clicking on the By Datasets and the By Points tabs. In the last page, we can also manually exclude or include selected data points. And the recalculated error function value is immediately shown at the bottom of the page. This was a demonstration that if the RKD format file that contains the detailed description of the experiment and the experimental results is available, then testing a mechanism against the dataset is very easy. Several hundred datasets can also be used for testing in a similar way, in a single run. The testing procedure can also be repeated with other mechanisms, and this way the performance of several mechanisms can be compared easily. Thank you for watching, take care.